Hi everyone. When it rains, it really pours, and sorry I can't be there. And I don't want to start a new unit like this, but due to some illnesses and some family things, I can't be with you. So hopefully this video will suffice. And again, like another good thing is you can always come back to watch it. I did want to give you this handout, but since I don't really wasn't able to really photocopy and get that to you anyways, what I have instead are a bunch of exercises that we will get a chance to try. If the substitute teacher did not get a chance to photocopy this for you for a period for the morning or in the afternoon, know that this will be uploaded. It already is uploaded on Brightspace, and you can take a look. Now, instead of just banking on this, I want you to, if possible, take out a blank sheet of paper and get a chance to practice writing your own notes, writing what you think is important and what you think is not important, don't write. That might seem a little unfamiliar or might shake you up a little bit, but it's actually going to be a taste of how I'm going to run calculus in next semester. I'm going to have minimal amounts of paper, like lesson handouts, but rather expect you to come to class and actually take notes with me. Okay, it's going to be a kind of a new way I want to deliver calculus. We'll see how that goes. But anyways, here it is. Okay, so to start off, the lesson is going to be called Radian Measure. That is chapter 4.1. Some of you might have heard this before, but let's pretend you didn't. Yes, it deals with circles and it's under the category of trigonometry, but let's pretend, once again, that you did not hear about what a radian measures before. And my question to you to start is, what is pi? Okay, and not this. Just think about it. What is pi? You might know what it is or how you use it, but where did it come from? What actually is it? Is my question. Okay, so it's not this, the pie is bad. Look at that fly. Okay, what is pi? Where did it come from? Some of you might know if you've ever been curious, but here is the quick backdrop story of it. Given a perfect circle, it has to be perfect. Not like this, but you get what I'm saying. Given a perfect circle, any perfect circle, if you were a person and you were deciding to travel all the way around it, the distance that you traveled, that is a circumference, would be directly proportional to how large the circle is, aka what's the diameter. So it has a direct proportion to the diameter. So someone long time ago was curious as to what that ratio was, and they started to experiment, as all good mathematicians and scientists do. So what they discovered was when they took a ratio, right, it was almost always equal to 3. In fact, it was larger than 3. It was 3 point something. But because of technology, it was a little bit hard to pinpoint. But as technology got better and better, they were able to dig deeper and they realized it was more 3.1. It was more 3.14. It was more 3.141, always. And it kept on going. And curiosity sort of gets the better of us. And with better technology, we started investigating, using a computer to do all the calculations for us. And to this day, there is no end to the ratio between a perfect circumference and the diameter of a perfect circle. And if you think about it, that's actually wild, right? I mean, a circle, you could imagine any simple person could, just using their creativity, think of a circle. But when you dig deeper to I guess the nitty-gritty details, there's something actually impossible that is made possible. Like a number that doesn't end is a ratio between these physical realities. Anyways, I find that pretty interesting. And a quick shameless plug, I have something for you. Just to prove a point, this is just a funny. This is what happens when math students are in charge of the pizza party. Ready? Taking the crust. What? 3.14, baby. You see it? Just a funny thing. But again, no matter what, as long as the circle is perfect, we see it every single time. Okay, here we go. Enough silly stuff. Going back to the actual math, here we go. So through this, we have confirmed that the circumference over diameter equals this number called pi, right? And of course, you know that diameter is the same as 2/2 of the circle, so 2 radius, right? And so this is where we get our equation or our formula that the circumference of any circle is equal to 2 pi times whatever the radius is. Does it make sense? There is a direct relationship between the circumference and the diameter, aka 2 radius. Okay, so why am I sharing this? It's important to know where pi comes from because that idea of pi, we have another use for it. And that is where we introduce this thing called radian measures. Okay, so here is another thing that I want to start talking about. Consider these rotations of a circular motion. So let's pretend this is sort of like a clock. I have an arrow and I have another arrow, a rotation of 0. But from this arrow, I have a small rotation. From this base arrow, I have a little larger rotation. From that base arrow, I have a much larger rotation. And I can keep going, right? And saying that it can go all the way around and back to where it once was as a 360 rotation. Like you know this to be 90 degrees. This is something I don't know how to guess. Maybe that's like a 30 degrees. Maybe that's like a 150 degrees. I'm just guessing. And this could be like a maybe 330 degrees. It's just random numbers. However, here is, oh, and maybe one thing. So a full rotation, just to hammer it out there, is exactly 360. So if I were to say 2 rotations, right, that will be 2 times 360, which is 720 degrees. You know, all this kind of stuff. Okay, but just as we said before that the circle, the circumference has a direct relationship with the radius, we can also argue that if we know the angular rotation of something, or the angle's rotation, like the degree, we also know how much we would have walked out of the entire circumference of the circle. Let me say that one more time. If you know the angle rotation, does this have a relationship to the distance you walked along the circumference? And I'm going to say yes, right? Think about it. If I have in a full circle, let's pretend, just to keep it simple, let's see, e.g., if I had a rotation of 90 degrees, in other words, that's a square piece right there. All right. And for simplicity's sake, let's pretend the radius equals 1. We have what I'm calling a unit circle. Okay. So R1 for simplicity, this is a unit circle. A unit circle simply means the radius is 1. If I have a unit circle of radius equals 1, then the circumference, which is 2 pi r, is the same as 2 pi times 1, which is 2 pi. I'm not going to insult your intelligence. If I walk 90 degrees what is my arc length? By arc length, I mean, what is the distance I traveled along the circumference? Well, this is a curve, right? We can call it an arc, sort of like an arc of a doorway of some kind of Baroque or Renaissance design. You know what I'm talking about. Anyways, what is my arc length? Well, we can consider, right? Remember, 90 degrees is 1/4 of a circle. So in terms of degree, it would be 1/4 of 360. But in terms of distance, it would be 1/4 of 2 pi times 1. And of course, mathematically speaking, of is a multiplication, and 2 pi divided by 4 would equal pi over 2. Right? So the degree, angle degree, right, has a relationship to the arc length. And people get sort of tired of calling it arc length, so we gave it a different word. Angle, the degree angle, okay? The degree angle, or the degree angle is directly related to the radian angle, or the radian measure. Okay, so radian, in fact, is a distance. The degree is the angle, but they are, I'm going to say, thrown around synonymously, sometimes to the point where it's a little confusing and they seem like they're talking about it in a wrongful way. It's so commonly switched between the two that you might get confused of what I mean by radian. A lot of the times you'll think, oh, radian is an angle, radian is a degree, but specifically, radian would be a measure of distance. Anyway, yeah, let's get to this. So before I move on with all the formulas and stuff, remember how we used a radius of 1? If the radius wasn't 1, but let's say the radius was 2, that means the circumference would be double that, right? So 2 pi 2, so that would be 4 pi. If that was the case, a circle, it would be 1/4 of 4 pi, which means it wouldn't be pi over 2, it would just be pi. Long story short, if the radius is multiplied by 2, the arc length is also multiplied by 2. It's very linearly proportional. If this is multiplied by 3, that will be multiplied by 3. And since it is linearly proportional, we as mathematicians simply don't want to deal with overcomplicated things. So by default, anytime we talk about radian measure, we pretend we are dealing with the unit circle. Okay? A full 360 degrees is always going to be referred to as walking 2 pi distance, or 2 pi radians around. If I'm dealing with 180 degrees rotation, we automatically assume it's going to be pi radians, or a distance of pi around. Okay, we're always going to talk about a unit circle, because if by some magical reason the radius happens to be 10, all we have to do is take our radian measure and multiply it by that same amount. Okay, so long story short, what am I trying to get at? Today, I am trying to get at you taking your knowledge of angles and always writing it as a radian. Okay, I'll say it clearly, and this is on video, so it's going to be permanent. In grade 12, you must show your work in radians, or you cannot get full marks, at least for communication. You can use degree to calculate it if you want, right? But any work that you show me, you must write it in radians. So if you're going to do that extra work anyways, why not take efforts to speak in radians instead of degrees for the grade 12 level? All right. So let's take down this definition. So if you want to write this down, you can. By definition, okay, a radian measure is the measure of distance around the circle. And as I said, e.g., if angle equals 360, then 2 pi radians is traveled. You can think about it like that. Okay, so that 2 pi radians, if we are talking about a radius of 1 meter, then it becomes 2 pi meters. If the radius is 2 meters, then that would be 4 pi meters. Whatever the radian is, it's multiplied by the radius. Okay, and I'll do another one. If angle is 180 degrees, then pi radians is traveled. Right? So notice this is not the radian itself is not a distance unit, but you can take that and whatever the radius happens to be it's very easy to calculate how much we traveled if we adopt this system. So me having this slightly hokey definition, Mr. Baird would probably be upset with me, but bear with me for now. It's going to be very easy to use just with this mindset. Here we go. But once again, just to continue, by definition, okay, radian measure of an angle theta, of an angle theta, of an angle theta is the length of the arc that, special word, subtends the angle divided by the radius of the angle. That might be a bit of a mouthful, so let me show you what that means as a formula. Okay, so by definition, a radian measure of an angle theta is the length of the arc that contains or subtends the angle divided by the radius of the angle. And this is the formula that you can copy down. Angle in degrees. Sorry. Angle in radians, sorry, is equal to the arc length divided by the radius. So, sorry. So theta in radians is equal to, at length, typically, I think in science, we like to do displacement or any kind of distance with the letter S over r. So I could be wrong, but I'm just going to write that here for now. In the same way, if I were to rearrange it, the arc length would be the radius times the angle in radians, or S equals r theta. That's essentially it. Today's goal is to do two things. Number one, you have to be able to go between angle and radians and vice versa. And also understand how to use this formula. It's very straightforward. I could give you some puzzling questions in a bit. Let's try some as practice. So if you do not have this worksheet that I'm going to switch over to, because it's not photocopied, know that it is available on Brightspace. If you do have it, awesome. Either way, let's do some together. So if the substitute could pause the video and let everyone sort of catch up to this. If not, if everyone's good, then we can move on. Okay, and switching in 3, 2, 1. Here we go. If you take a look at this, the back part of this sheet, it says, convert each degree measure into radians. So I actually provided a conversion factor to help you. Just as you know, 360 is directly related to 2 pi, that is a 1 full rotation. We can simplify saying that 180 degrees is equivalent to a pi rotation, pi radians. Okay. And so if you want to convert between units, you need to have a conversion factor. Let me demonstrate. For A, 35 degrees, I want to turn that into radians. How do we do it? Well, we multiply it by a conversion factor. And I'm sure you practiced this from grade 9 science, but in case you forgot, here's how you do it. You want your degrees. Right now, the degree is in the numerator. If you want to cancel out that unit, we need to divide by a degree. So place the degree on the opposite side of a fraction. So if it's a numerator, write denominator. And if 180 degrees is in the denominator, its equal counterpart, pi radians, is written on top. And once you simplify, this becomes 35 pi, because degrees disappear, degrees cancel out, over 180 radians. What does that simplify to? Divide top and bottom by a 5. You get yourself 36. 7 pi over 36 radians. And that's a little weird. So how about we do a degree that might have a nicer number, like that. 150 degrees. Conversion factor, pi over 180 equals 5 pi over 6 radians. Okay, cleaner. Oh, I have a sneeze. Excuse me. Okay. Please get as comfortable as possible converting degrees to radians, because we will be using radians quite often from now on. In the least, please commit to heart the degrees 0, 90, 180, 270, and 360, along with 45 and 35, 225, and 315. And that would be level 2. Level 3 would be getting the 30 degrees and the 60 degrees counterparts as well. So that would be 120, 150, all of these in radians. That would be the ultimate goal. If you can do those, you're in a really good spot. Okay, so in the least, I hope you get a chance to try 135, 150. I'll just do this. 210, 225, 240, 270, 300, 315, 330, sure, 345. Like the ones that are in 15 or 30 degree increments, basically all of these. Okay, would you please, 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 please practice those? All right, the vice versa portion. Pi over 18. As soon as you see a pi in a angular measure, you know that it's going to be in radians. Even if it doesn't say radians, you can immediately assume that the unit is in radians. So these are all in radians, okay? If the unit is in radians, what do you multiply by? Well, because the radians, let's say, is in the numerator, you put pi radians in the denominator, and you place the degree counterpart in the numerator. You divide. So pi divided by pi is a 1. And 18 divided by 18, 180 divided by 18, this is equivalent to 10 degrees. Pi over 18 is equivalent to 10 degrees. Okay, this is a special one, so I'll do it with you. 3 pi over 4 radians. If I multiply the conversion factor, okay, pi divided by pi, bam, bam, and 418, that is 45. 3 times 45, that's 135 degrees. That's a very special angle. It is right there. Okay, in quadrant 2. Please practice all of these. Get used to it. Some of these are really messy. Some of these are very clean. Regardless, trust your math. Make sure you practice all of these. And lastly, finding the unknown arc length or angle using the given information. Are you ready? Please recall that the radian measure is equal to the arc length. So we call that S over R. And as rearranged, the arc length is equal to the radius times the radian measure. Here we go. For A, angle is 0.8 radians. The radius is 12. I have r, I have theta. I'm looking for the arc length. This one, S, is equal to 0.8 radians times 12. This is going to be 9.6 radius is centimeters. So the arc length is also in centimeters. Okay, so if you're wondering what the heck I am doing, recall that pi is equal to 3.14 radians. So 0.8 radians, pi is 3.14, and in a circle, that is equivalent to 180 degrees. 0.8 radians is going to be closer to about here. So this would be 0.8 radians. If the circle had a radius of 12 centimeters, then this portion right here is approximately 9.6 centimeters. That's what this question is telling us. Let's do another example. How about D? For letter D, the angle is 2.1 radians. The radius is 1.2. So by process of elimination, I am looking for the arc length, which is r times theta. That is 1.2 multiplied by 2.1, which is something I unfortunately need my calculator for. 1.2 times 2.1, that's 2.52 centimeters. What does that mean visually? It means if I had a circle, my radius was 1.2 centimeters, and I rotated not a full 180 degrees, but 2.1, which is around here. If I rotated an angular rotation of 2.1 radians, that means because the radius is 1.2, the arc length is going to be 2.52 centimeters. That's what this is. Okay, chew on this a little bit. It is definitely a new concept for those who've never seen it before. Please, please, please practice. And when I see you next, I hope that you'll be ready and able to start talking about trigonometry and angles and triangles and whatnot using radians and not degrees. Best of luck. Please practice your heart out, and hopefully everything at home on my end will be good. So I'll see you on Monday. Okay, have a great weekend. See you then.